What's up, what's up? Welcome back. Today we're working on my operating system, an x86 operating system titled Stream OS for now, because it's an OS that I've been writing on Stream. And what we're working on today is enabling multi-core support. So we've kind of been laying the groundwork for a while now, maybe about a week, trying to make sure that our operating system is in the state where everything is supposedly safe for multiple cores, or to run for multiple threads, synchronized using atomics. We've kind of done some preemptive work to get handles to the things that we need in order to start actually working with multi-core. And today what I want to do is actually try to run some code on the second CPU. So what is this OS? Well, right now it's kind of just a little bit of a kernel. It's written in Rust. And if I do a quick little run here, we see that we boot in a virtual machine. We have some sort of logs that are written to the serial port, which with running through QEMU are redirected to standard and out. We have a logging infrastructure. We have some sort of graphics as well as user input. So I'm using my keyboard to move the paddle around to bounce this ball around on screen. And then we have some sort of network stack. So if I try to netcat into my thing at this specific port, I can say things to my OS and it'll send it back. So just little echo server, just to prove that we have our Ethernet stack working, which involves ARP, TCP, Ethernet, PCI to work with the Ethernet card, etc., etc. We have some form of concurrency because we're doing this in the background of this game, so both of these things are happening at once. Yeah, and so that's kind of where we're at. It's all written in Rust because that's the language I feel like working in right now. And yeah, so what we did last stream was we got these handles to these advanced programmable interrupt controllers, which, if I understand what I've been reading off stream correctly, is the way that we communicate to other CPUs from our boot CPU. So from the docs I've read, we have one CPU that's our bootstrap processor. This might be CPU 0. I would guess that in QEMU it will be CPU 0, but this is the BIOS can choose whichever core it wants to use as the boot one because they're all kind of symmetric. And attached to this guy is this advanced programmable interrupt controller. This guy sits on some bus, and all the other CPUs also have this same thing, APIC, advanced programmable interrupt controller. And these guys they call application processors, AP. But there's nothing really different about these guys other than that they aren't the one that booted. And what's going to happen is I'm going to send a message out on this bus. And I'm going to say hey, can I boot CPU ID 1? I've got a list of CPU IDs that have been pulled from the BIOS. Theoretically, we kind of proved last stream that we can find those. And that we get a list of CPUs that at least correlates with the number of CPUs that we provided to the QEMU virtual machine. And so we can iterate over these and say hey, can you turn on? And there are a few signals that you can drop on this line that will either put will reset the CPU and put it into a not running code state, but an initial state. And then there's another command you can use to actually start running code. And in there you kind of inject where on the CPU where in memory you want to start executing code from. And I think that we should just be able to iterate over these CPUs and initialize them all one by one. So I think I'm going to be kind of following this symmetric multi-processing thing. Hold on, I had a document that I wanted to open up as well here. Is it Intel multi-processor spec? Yeah, okay. So at some point Intel goes, hey, we have multiple CPUs and they're all different. Let's make sure that we have a standard for how to work with these multiple CPUs. And the part we're looking at here that's important is this is what they say you should do. Is that they say you should send this like initialization instruction over the bus connected through to the apex, wait for some amount of time, and then start sending the startup sequence, which might involve sending a startup twice. Hello, everyone. Hello. Reading through this like OS dev page on this stuff, I saw somebody talk like they talk about how getting a like clock that's as precise as needed to send these 200 microsecond delays is like kind of difficult. So in their startup code, they do some sort of like external synchronization where they try to see if something succeeded. I think I saw somewhere that they have this like flag that they set to synchronize between the AP running and application processor running and like the BSP bootstrapper processor saying like, yeah, I'm good to keep going. So we'll probably take a look at that here, or we'll like take a little bit of a deeper look at that later. And I saw somewhere they say like this avoids some problems where if you double init your processor, you might actually, in some cases, restart the same code twice, which could result in like it might look to your system like the processor just like fucking died mid startup, or you might like to your system think that you have twice as many cores as you think you're supposed to. I think I saw that here. If it doesn't increase this counter within a few milliseconds, I send the second to CP. This is different to Intel's thing where they say 200 microsecond delay, blah blah blah. Clocks are hard to accurately measure so early in boot. And I found it on real hardware. If the delay is too long, then an application processor CPU can run the OS's early AP startup code twice, which would be a problem. Yeah, so that's what we're looking at today. I think what I want to do first is I just kind of want to like walk through how the OS dev wiki is like suggesting that we start up, how we like start up the CPUs, and what we do on each of the CPUs initially, just to make sure that we understand it, and then from there we can start trying to like implement ourselves. So that's the plan for today. So what they have here is they have some flags talking about keeping track of which CPU is the bootstrap CPU, whether or not we've fully initialized, I guess. Bootstrapper done. Check how many application processors have started. Here they just use a little bit of assembly to pull out the ID of the CPU that we are running on. Cool. They has copy AP trampoline code to a fixed address and low conventional memory. So I think that this is this assembly that they write down here that like they want to initialize. They want to use to like initialize the CPU and start running like normal C code. In our case, it'll be Rust code, but whatever, it's the same shit. He's saying that they copy it from a known address to like wherever the linker stuck it to a fixed address at like 0x8000. I think I read somewhere that this is because when the CPU boots, it's going to be in like real mode, which is like a really funny name actually. I've never really thought about that, but yeah, what is it? Real mode CPU? Which is a simplistic 16-bit mode of operation that is present on all x86 processors. The mode we're running in is protected mode, I think, which is like the 32-bit mode. So if I remember correctly, it's something like you boot the CPU, it starts in 16-bit mode, because like once upon a time, long time ago, they had 16-bit processors. And then they're like, shit, we want to make like 32-bit processors, but like we already have all the 16-bit code. I guess we'll just start in 16-bit mode. And with our current setup, the BIOS will switch us into protected mode for us, so we don't need to worry about that. But when we boot the other CPUs, we don't have. Sorry, I shouldn't say the BIOS. Sorry, the bootloader, I think I said bootloader, I can't remember now. The bootloader puts us in like a good state before launching our kernel, but we're not going through the bootloader for these other guys. So we have to put them at a low memory address that is accessible in real mode, as well as start with 16-bit code before jumping into the 32-bit code. We'll get to that in a bit. So they get a list of cores that they don't talk about how they grab here in this code sample, but we've kind of proven that we know how to do this last stream, which is by like walking these ACPI tables. The ACPI tables has like a list of APIC IDs, which correlates with CPU IDs. I think maybe even specifically list them. Let's double check that. I think that's in the MADT table, multiple APIC description table, and one of the things that we found in here was ACPI processor ID. Great. So here that we have number of cores, they check if the APIC ID is the boot processor ID, because we don't want to reboot ourselves. That would fuck shit up. And then what? They'll do some like register writes here. So they're writing a 0 to 0x280, which I think will be shown here. We should have our registers for the APIC here. So 280 is error status register. And over here, they are clearing it. Let's just put these two pages right next to each other so they're easy to jump back and forth between. Here, he's writing something to address 310 where he's saying, like, what the fuck? He dereferences address 310 and he masks out the bottom 8, 16, 24 bits, and then he ORs that with something at bit 24. So he's saying, like, select this AP. So that is a write to address 310, which is the interrupt command register. Is there somewhere where in here it tells us what that is? Here. So here he's setting bits 24 up, so he's masking off, I guess, these guys and setting the processor ID. So I don't see that written in here anywhere. Interrupt command register, which I think is supposed to be 300. Yeah. So it's 300 to 310. The interrupt command register is made of two 32-bit registers, one at 300, one at 310. It is used for sending interrupts to different processes. The interrupt is issued when 300 is written to, but not when 310 is written to. Thus, an interrupt command one should first write to 310, then to 300. Cool. At 310, there is one field at bits 24, 27, which is the local APIC ID of the target processor. Oh, and here's how 300 is structured. What about 310? There's one field. Oh, so they're kind of saying that, like, this is indicating that the upper half only has one field, or they're saying, like, the other fields don't matter. Sure. Probably somewhere there's, like, more official documentation on this, but that's fine. I'm okay with understanding this. So understanding this at this level. So this level, they're saying, take what's already fucking in there, and then mask out the bits 24 to 27 and write my shit. And then here they send this like init IPI by writing to 300 after they've written to 310, like it says here. And the init IPI, they're saying, what do? They take the top bits already because these are reserved. I assume 20 to 31 is what they've masked off here. Let's see. So they've written, what is this? 1, 4, 8, 12, 16, 20. Yes, they've taken like the reserved bits and they've leave them as they are, right? And then they've set the lower bit. So C50000, what's that look like? We can probably open up Python. One sec. Beep boop, beep boop. And what do they have in here? What's the number we said? 0xC500. And we want to format this as Boolean, or sorry, not Boolean. What am I trying to say? Binary. Thank you. Brain. Jeez, slow down. And so this is what? Bits 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15. 8, 10, 14, and 15. So here they're setting some priority mode. And 5 is init. So that's what we saw there. So 8 to 10, we saw the number 5 for init. And then clear init level for tsert. So there's some sort of like, this is init stuff. Great. And this is saying that they're triggering an init interprocessor instruction, I think is what the IPI stands for. If not, we made it up, but it's a good enough mental... Whether or not that's correct, we can pretend it's correct. It's close enough. And I don't know what the fuck this is saying. So they say while we read the value at 300 and bit 12 is set. What is bit 12? Delivery status cleared when the interrupt has been accepted by the target. I see. So we wait for the delivery. That's what this says here. Wait for delivery. And what is like, I've never seen this like pause before. ASM pause instruction. What does this do? Does this just compile into like a no-op? What's the difference between this and just like a no-op thing? The conditional branch will never be taken and the pipeline will fill in with compare instructions. This goes on until finally another processor, blah, blah, blah. Whenever the processor sees an external write, it searches in its pipeline to see which speculatively accessed the same memory location didn't yet commit. If any such instructions are found in the speculative state of the process, it's invalid and erase each pipeline push. Okay, so the pause instruction depipelines the memory read, so the pipeline is not filled with speculative comp instructions, like in the first example. That seems reasonable. Okay. Sure. Of course, depipe will also waste less energy in the spin lock case. Sure, because, yeah, that makes sense. Okay. Okay. Cool. So he's saying pause to wait. I wonder if, like, I just do, like, a while loop in Rust with volatile reads. I would think that the compiler would do the right thing there, but maybe not. We'll find out. Maybe we'll try that later and see what happens. Okay, so he waits for the delivery. Then I see. So he sends this like init command, which is so I see. So he has to be I think he's basically setting this flag that says like turn on this line that like sets the init flag that's plugged into the CPU is how I'm thinking about this. And then he waits for some period of time until the other side has acted that init flag. And then he goes, okay, good enough. I'll turn it off now. Cool. Then he waits for 10 milliseconds, microseconds, milliseconds. That's got to be milliseconds. And that probably lines up with this thing from the Intel multiprocessor spec that says you have to wait 10 milliseconds. Cool. And then here they send the startup sequence twice, or the startup instruction twice, without waiting for delivery like they did on the first one. So they just like blast it out. Oh no, here they do wait for delivery. Okay. So here, clear errors. It's kind of weird that they clear errors because we never check for errors. So it's like, why bother? Then they select the thing again. I'm kind of surprised that every time they write this, they have to reset the application processor again. But sure, fine. And then they send the startup sequence, wait 200 milliseconds, and then do it again. 200 microseconds and do it again. Now, somewhere they say that this is... Where is the stuff on, like, wait for the application processor running? I don't see anything about, like, AP running count. Oh, now you'll have the number of running APs and AP running. So I was under the impression that when I read this earlier, somewhere it was saying that this isn't how, this shouldn't match the Intel spec. You'll realize they do not keep the standard. When you're testing, you must not do broadcast APs nor broadcast CPs. The following example has a decent amount of error checking to be used on real hardware. It needs these variables. Okay. Sure. So I think I read, maybe it was in this forum post. This guy's saying, Brendan, who seems to be some sort of like OS dev wiki, like, I don't know, people just like mention him by first name, like he's someone I'm supposed to know. Like, hold on, Brendan. Yeah, Brendan offers an alternative method, which should be done for each application process individually. First, send an init, wait 10 milliseconds, and send a CPI, then pull for a flag to be set by the AP's trampoline code with a timeout of 1 millisecond. If the timeout was reached, then send another CPI and pull for the same flag. So I guess this example code is following closer to what the multiprocessor spec says, but I think that this kind of makes sense. So that I don't have a clock of microsecond accuracy. I have a clock with a 4 millisecond tick period. We have 256 hertz. So I will probably end up doing something that's closer to what they say to do here, which is just wait for 1 millisecond and check if the flag was set by the application processor, and if not, then you need to send a second one to start it. Because I think that there's just some CPUs out there that need 2 and some that need 1. Great. And here in the startup sequence, I think they inject the actual address that this code has been, the like trampoline code has been written to. So where is that? This must be the lower bits here, 800 or no, this 608. Let's see. Bit 0 to 7, so the starting page number for CPIs. Yeah. Where page number is probably in like units. I guess it depends on the page size. Which we'll have to figure out. But based off of this, the fact that they just write an 8 in here kind of indicates that it's times 1000 hex for page size. What is that? Does that line up with something that I've seen before? 16K? 4K page size? That sounds right. Memory. I'm pretty sure I've like seen that somewhere. Oh, wait, yeah, 4 kilobytes? Where the fuck did that go? Ugh. Wikipedia, yeah, I get it. You want me to pay you. Anyways, I'm pretty sure I've seen 4K a lot of times. They're like using it as an example here. I'm pretty sure I've seen that. And that lines up, that makes sense. So I guess we'll try that. And I guess that also lines up with why you need to put this in the like very low at memory addresses, because you only have up to 0xF0000. Cool. Okay, so now what the fuck are they doing in like application processor initialization? So they call this a trampoline. I think my guess is that trampoline is like a kind of like joke term for we're going to execute jumps in here to jump into like a normal function context in like C code or Rust code in our case. And so a trampoline is like gives like somewhere where you jump. That seems pretty fun. Good little name. So they do this like interrupt clearing shit. L jump to this address, which is here probably, with 0 in here. So I guess if I remember correctly, this is the syntax of a jump that uses the GDT, like it like does like a global descriptor table lookup, and uses that. I don't understand why this is here though, because we haven't set up a global descriptor table yet. Here is where they're actually setting it up. So they're just saying like, presumably, I'm not gonna like look too closely at this, but I'm assuming when they say flat code, flat data TSS, they're just kind of like putting in memory ranges that are sane here initially. We might be able to actually like store our existing GDT in like global memory somewhere and try to load those off rip. That'd be kind of cool. Then they're saying jump to Xerx 8040, which I guess is this guy. I don't know what this. I think that this is maybe you need to set. We'll come back to this. This is like global descriptor table stuff that needs to be done. That we've done on our Bootstrap processor, but will have to be done again here. Here, I think that's doing like an XOR of something with itself clears it, if I remember correctly. Like 32 XOR 32 0 1 2 3 XOR 1 2 3 0. Yeah. So that just forces it to 0. They put 0 into DS. What, like, this is AT&T syntax, so it's source dest, I think. I think the first thing is the source and the second thing is the destination. Yep. That lines up. So I wonder, why not just write, like, do an immediate load here? Maybe because you need to move from register to register for 16-bit loads or something. So what is, like, %ds again? There's... I think I remember seeing that as, like, the 16-bit value. GNU AS... %ds? Will that just tell me? x86 assembly syntax. This is where I just was. DS register. We're back to the same place again. Fuck. It's frustrating that I don't remember. Here we go. High and low registers, maybe? Nope. x86 registers. GNU AS maybe will tell me. Registers. Here we go. This is close, so we have like lower bits, upper bits, 8 bits. But what is DS? That's not in any of these. Okay, whatever. We'll maybe come back to this. Or maybe this is a specific register. That's actually ringing a bell. I don't know, we'll come back. Then they're moving this into SS. Oh, yeah, I think that these are related to the descriptor table. Hold on. Where this must be in my code somewhere already. Yeah. These were special registers, if I remember correctly. DS, ES, FS, GS. Segment registers. Here we go. DS holds the data segment that your program accesses. And then these are the segment registers and the stack segment. Yeah. So they're saying, put 0 in the data segment register, then load the global descriptor table here. So here these are like the segments, and then here they're putting pointers to the segments or something. Move CR0 into EAX. What's CR0? CR0 register x86. Control register. The fuck is that? This doesn't look familiar. It contains the address of the segment table for dynamic address translation. Okay, cool. That makes sense. Then they're setting the value in EX to 1. Right, because this should be segment 0 at this point. Or maybe we don't know what segment we're in. They're like setting it to 1. the lowest bit, and then they're moving it back, and then they're doing a long jump to this location. So this long jump reloads the like segment of the GDT that they wanted, I guess. And probably this L jump brings us to from 16-bit to 32-bit mode. So probably here, entering protected mode, they like load a descriptor table. They set the protection enable bit in the control register, and then they put it back. This is Intel syntax, not 18 syntax, so it's going the other way. And then they perform a far jump to enable 32-bit mode. Okay, cool. So that lines up. And then we're just in 32-bit mode, and we do like our normal initialization. So this is going to look very similar to what we have in our boot assembly. So basically all we do in our startup script is the wrong word here, in our startup sequence is we set up a stack. So what we've done here is we've like allocated a 16K stack. Just like we've just stuck it in static memory. And what we do is we just say like, hey, before we call our kernel main function, like initialize our stack. That seems to be what they're doing here, except they have to offset their stack by the CPU ID. So presumably this like CPU ID instruction will give us I don't want this, I want this. Returns the processor identification and feature information to the EX, EBX, ECX, and EDX registers according to the input value, blah, blah, blah. Jesus, this is complicated. But I'm assuming that what they're trying to get out of here is just the ID. So they've put 1 in EAX. So input EAX equals 1. Returns model family step information. What is stepping ID? The like CPU ID? Stepping IDs are provided as needed. Okay, let's see. What are they reading here? They call CPU ID and they shift 24 in EBX after. So after they put EAX1, what do they put in EBX? When CPU ID executes with EAX set to 1, additional information is returned to the EBX register. Brand index, number provides an entry into brand string table, which brand strings for ID 32. I don't care about that. High byte of EBX. This number is the 8-bit ID assigned to the local 8-bit during processor power up. Cool. So they're grabbing like a CPU ID. I think we can maybe assume that they are 0 indexed, but maybe not. And they are using that as part of their stack. So hold on. So they shift EBX right by 24. So they're filtering out only the CPU ID. They stick that in EDI. Why? Oh, so that later they can pass it as an argument to the AP startup function. Cool. And then, I see. So they shift it left by 15, which should put us in a 32K aligned stack segment based off CPU ID. Hold on. So if I understand this correctly, they're going to have like memory. And what they're doing is at every like 32K, like here, 64, what's 32 plus 64? 96K. They're saying that like, we'll take the CPU ID and we'll shift it left by 32K, by 15, which should give us 32K aligned indexes. And they're basically saying like, if I'm CPU ID 0, my stack starts here. So this will be like 0. If my CPU ID is 1, my stack will start here, and if my CPU ID is 2, my stack will start here. So we end up with like CPU 0 stack, CPU 1 stack, CPU 2 stack, etc. And so I guess that probably also means that if I overflow from stack overflow on one CPU, that's actually just gonna like fuck up the stack of another CPU, which is gonna be fun for debugging later if this is how we end up doing it. And then here they have stack top, which I guess they're assuming that we've defined in our BSS already, which we have in our boot script. We have this like stack top thing. And so we're just going to have to like increase the size of this thing significantly for a number of CPUs. And presumably we have to allocate enough for how, I guess we don't know how many CPUs we're going to have. So maybe there's like some form of like dynamic allocation that we should end up doing. But for now, what we can do is we can assume that we're only booting with like maximum n CPUs and just allocate that much stack initially. And if there's like less, if we allocate enough stack for like 8 CPUs and there's less than 8, well then like we can go fuck ourselves. Or there's more than 8, we can go fuck ourselves and we'll figure it out later. Maybe we should also like refuse to boot up more than a certain number of CPUs in our like initialization stuff. So they set up their stack. They push the CPU ID onto the stack so that when they boot, or sorry, when they call the C function, that'll be like the first argument that's passed in. And then what? Then what do they do here? What is this like? What's going on here? So they wait for the BSP initialization to be finished for some reason. Not sure why that is. And then what is this lock instruction? I've never seen this before. Presumably this is just a atomic instruction. Lock is not an instruction itself, but an instruction prefix, which applies to the following instruction. That instruction must be something that does a read, modify, write. Yeah, okay. The lock prefix ensures that the CPU has exclusive ownership of the appropriate cache line for the duration of the operation, and ensures that additional ordering guarantees. Yeah, so this is just like some assembly level atomic operation shit. And then once here they're happy that they've that the BSP initialization is complete, and they're ready to jump into C code. Then they jump to C code. So I'm not really sure why. I think my gut says I'll just fucking skip this. Because I don't see why I shouldn't start running code on one CPU before all CPUs are initialized. Yeah, I see no reason why that matters. So okay. I think I have a pretty good handle on what's happening here. This is like iterating through CPUs and launching their like getting them running a trampoline, and then our trampoline just takes us from 16-bit to 32-bit mode, and then initializes a stack and calls our C function. Pretty straightforward. Straightforward. Yeah, okay. So let's, I guess, just start trying to implement that. So I already know that I have some things that I want to do differently from here. This like mem copy into the low area of memory, I think that's bullshit. And I would think that we could just make our linker script shove the code there. And then I guess the first thing to do is just try to like do something similar to this for one CPU and see maybe in QEMU, we might be able to like set it up with GDB and get it just jumping to a specific address. And then maybe we could like breakpoint that the CPU has actually made it there. That seems pretty reasonable. I'm going to take a quick break and go to the washroom, but I'll be back in like... Alrighty. Okay, so I guess the first thing that we want to do is we want to just get our own CPU ID. So yesterday we got to here where we got the ID, the APIC IDs. So maybe let's just do everything in here. This is like our parsing of the ACPI tables. And I think I'll just comment out some of this stuff so that we have like a nicer place to start from. Okay. Comment out like this shit. And here, I think that now when I run, we should just see the APIC IDs printed here. APIC ID 0, APIC ID 1. Cool, so these are the, we do have, this indicates we have like 2 CPUs plugged in, and I think that's right. If I look at our QEMU wrapper script, we have -SMP2 for symmetric multiprocessors 2, and if we put in 4, we should see 4 of these. Yeah, we say APIC IDs 1, 2, 3, and 4. Great. Now we need a way to like get our CPU ID. So I don't know where this is gonna live yet, so I'm just gonna shove it in here for now with like a fix me stick somewhere appropriate. And we're just gonna call this like function CPU ID. And this is gonna return either 2, maybe a U8 or something. Let's say U8 for now. And we're just gonna try to do like this same shit here, which looks right. So, like we were reading, they want to do a move 1 into EAX to put before calling the CPU ID command, because depending on EAX, it's going to switch behavior, and then we're going to read the values in EBX to get the registers out. And we're probably going to have to mark that EAX, EBX, and ECX and EDX are all fucked up by this. Let's just double check this. Yeah. So here we have what? ASM core x86 core arch ASM. There we go. So this will execute some assembly, and it's going to take in a like assembly string that to execute, as well as there's like some sort of like syntax for marking input and output registers. So let's see, assembly macro rust is probably where we're going to look up the parameters there. And they have inputs and outputs. Okay. So here, I think you can also specify specific registers. I think I probably have a example of this in this function here. Yeah, so I have in registers and out registers specific addresses. So here I can say out EAX, and we know that this is going to modify returns information in EAX, EBX, ECX, and EDX. So we just have to mark all of these as output parameters, even though we're not necessarily going to use them, because that's going to fuck shit up. We want to set the EAX input to 1. And here we're going to call CPU ID. And I think that might be it, because we're not doing this shift right shit, and we're going to pull EBX out manually using the Rust syntax. So here we're going to say let EBX is equal to 0. And here we're going to put this into the EBX register, I think. Is that how this works? The output parameters. Where does temp go here? Oh, they put temp here. So they store this in temp. But they don't actually have... Oh, they don't care about the value. Yeah. Okay, so this works. This is right. So here, this is going to set the value of EBX to this EBX variable, and then we should be able to say EBX shifted right by 24. as U8. This has to be mute, and this has to be unsafe. I wonder if there's like a QEMU option to change the bootstrap processor so that we can prove to ourselves that this is right. Right, so let's just say we'll put in this random print entries functions, we're going to say CPU ID is this. And then we'll call CPU ID. So presumably we'll get 0. Yeah, and I wonder if there's like QEMU change bootstrap processor. It would be nice to prove to ourselves that we are actually getting what we want to get here. This doesn't do it. Maybe we'll look it on Google instead of DuckDuckGo. Multi-process QEMU. QEMU change BSP number. BSP processor. I wouldn't be shocked if it just doesn't let me. It would be cool though. Okay, whatever. We'll just leave that as is for now and kind of hope to God it's right. I guess, let's at least print out what's in EBX to see if we, get something. Or maybe we'll say that this is, not 0U32, and at least prove to ourselves that we overwrote it correctly. So let's print out here. We'll say EBX is this. So we are getting something in here, and let's kind of like at least look at what this CPU ID instruction is supposed to return in EBX. And maybe that will give us some guesses. Brand index. This number provides an entry to the brand index string table. That's not, I don't really want to look at that. Cache line size. Yeah, I don't know. It's giving us a number that's not the number that we initially set. And it's giving us CPU ID 0. Fuck it. Let's just hope that that's right for now. Okay, so that's this guy out of the way. So we're going to iterate over each local APIC entry, which we have done here somewhere. So here we are iterating over entries, and we are getting APIC IDs. So I guess for each APIC ID here, we'll say let BSP ID is equal to CPU ID. And then here, as we get for each index here, we can say let APIC ID is equal to IT add 3, right? That's what we have down here. And we'll say if APIC ID is not equal to BSP ID, boot APIC ID. And then we can put all of this boot stuff here. And this takes in a ID as a U8. All right. Okay. And I guess we also need the APIC pointer, which is going to be... Oh, what do they make it? I don't know. We'll find it in here. Okay, so I was going to say that we can just pass this in here and boot these as we go, but I guess we don't know that we have a valid APIC pointer until later. Right, because we're getting the APIC pointer by walking this APIC table. Here we have processor ID and ID, but we don't have like the pointer to it. Where did we get the pointer to it? Oh, here. I see. That's up above. So we should have this here. Cool. So this is going to be what, a like, we'll just call this like a U32 pointer, I guess. And here we're going to pass in self.local apic adder as mute U32. I think that's what they said it is. I think somewhere in here, the interrupt command register is made of two 32-bit registers. I guess making it a U8 is going to be easier to work with, though, because that means that our offsets are going to be in the we expect. Okay. So we'll say what? We'll say that the error register is the apic pointer offset by 0x280 as mute U32, I think. Let's see. The 0x280, yeah, they are casting it to a uint32 here. So we'll put this in unsafe. And what else do we have? We have the interrupt command register. So here we'll have the ICR high is this time plus 310, and ICR low as this plus 300. And what do they do here? They select the pointer, the EP, trigger init. Okay, so let's do that. So we'll say let high val is equal to ICR high read volatile. That's this shit here. Then we're going to change this to high val and equals 0x ff. So say keep, this is keeping existing values, but setting and removing processor ID. Then we set our high value or equals the ID as a U32 shifted left by 24. Right? That seems like this. That's what they do here. So we'll say set CPU ID, and then we ICR high, bright volatile, high value. Great. So that is this, and then we trigger an init. Which is going to be, we read the low bit. So we say low val is equal to read volatile of the low thing, which is this. Then we save reserved upper bits. So low val is equals to 0x FFF, I think. And then however many zeros this is. That seems reasonable. And then they set this value, which is an init interprocessor instruction. Then what? Then we write this back. Like this. Okay. Then they wait for delivery. So we'll say loop. We'll let delivered is equal to ICR low, I think. Yep. Read volatile, get bit 12. And if delivered, break. That's essentially this. Now we're going to do the same thing. So where we set the select the AP. So I'm actually gonna factor this out into select AP. So it's going to take an ID as a U8. It's going to take the interrupt control register high portion. And that's just womp this stuff. And this is an unsafe function. And so then we can say select AP ID with the ICR high. And we're going to do that again down here. And now they're going to deassert. So here we're going to take this same thing. We're going to say this stuff to get the value and then keep the reserved bits, but then set this instead to deassert, I guess. And here we're gonna make another function wait delivered. Wait IPI delivered. And this is gonna take in the low half of the interrupt control register. And that's just whoop, this guy here. And where did I take that from? This is here. Wait IPI delivered. And this is ICR low. All right. Cool. Here they're clearing the error register. But I don't really see any need to do that. Because it's already treated. Like, sorry, we never read it, so why do we care? Right? Maybe the APIC won't behave correctly if we don't set it, but that's okay. Now what we're gonna do is we're gonna have to wait for 10 milliseconds. So we're actually gonna need to get like a reference to our clock in here. So we'll say wait 10 milliseconds. And we'll deal with that later. Fuck it, we'll deal with it now. So here we need a reference to our monotonic clock. And here we'll just say what? Let start time is equal to time get. We'll say let end time is the start time plus 10 milliseconds, which is 0.01 seconds times time tick frequency. Let's just double check that this is reasonable. So we have tick frequency is in ticks per second. Here we have seconds, so we're getting ticks. So multiplying is right, and we have the start time is a tick. Cool. So this needs to be as F32. And then we say end time is a rounded up version of end time. So end time dot seal as usize, I think is how we're tracking time here. Yeah. No seal. Oh my god. Is there really no... How did we do this before? We did like... There's like intrinsics in Rust. So I think that what happens is like the seal function is implemented by libm, which doesn't exist because we're in our own operating system, which doesn't have libc and libm. So I think that there's like an intrinsic that we use instead. Intrinsic. Core intrinsics and seal F32. Here we go. core intrinsics f32 was seal f32, and this takes in the end time. Okay. Cool. And so now we can just spin until we hit the end time. So we said just say loop, or we just say while time.get is less than end time. And that's a 10 millisecond wait, baby. Okay. What's next? Then we send the startup IPI twice. And here's where we're going to try to start taking some shortcuts. I'm going to hope to God that sending this once is enough to boot the QEMU CPU. And fingers crossed on that. And hopefully if we do that and then just run GDB, we should be able to see the CPU like initialize and jump to somewhere. So let's just do that. So I guess we can send it twice. Blaze it. I don't know. We'll see. I guess we can also see what QEMU does here, but we'll save code spelunking in QEMU for if it doesn't work. Okay, so here they read 310. They select the AP again. And then they trigger a startup. What a weird... we're going to look up what this mask is for later, but for now, we'll say, select AP. So here we should say, let mute low val is equal to ICR low read volatile. And this should say, dinit. And here we say low val and equals this, and low val or equals this, and we'll just write startup IPI because I don't really understand it yet. We'll figure that out later. And I think that's enough. I think we'll see. And what I expect to happen is there'll just be like random shit at address 0x80000. But if we open it with GDB, hopefully we can put a breakpoint at that address and just kind of see what happens. So I think we can do cargo run release. He's mad because boot APIC needs a monotonic time, which we don't have. He also should take a reference to it, by the way, so we'll just hook that guy on there. Here we need print entries to take in a time. Where print entries is just like a terrible misnomer, but that's okay. We'll deal with that later. And this guy is called from here, which will now need a time. And this guy now is going to take in the monotonic time. All right. So what doesn't he like here? Undefined reference to CLF. Fuck. Undefined reference to CLF Rust. Let's see. It's part of the laugh. Fuck. Do I really need to no STD CLF Rust? How to access methods like this in no STD. libm has a lot of replacements. Fuck. That's annoying. So if I don't have libm, do I just have to like manually implement this? How? All right, fuck it. We'll get a little crazy here. So So we don't actually need CLF. We can just do end time is equal to end time plus 0.999, as he says, or something. Right? So this will just be like, this will get us to the point where hopefully most of the time it rounds up. Obviously it's not perfect, but I'm not really worried about being that perfect. We'll just throw another couple lines on there, fuck it. All right. Oh, we never assigned low val here. Oops. ICR low right volatile. Low val. There we go. Okay. What next? Cargo run release. Okay. And the fact that we crash here is probably a good sign. GDB equals 1. So that we run our like wrapper script with GDB enabled. And then I think here in this window. Hello, there we go. In this window, maybe we can launch GDB with our script. So maybe we just comment these out for now. Or delete them and say GDB-X run GDB. Okay, and like what's going on here? How can I like check CPUs? Threads? Info threads? Oh, okay. So we have these like named CPUs, and I guess why does this crash now when it didn't before? So it's in a copy somewhere with an unknown thing. So he must have jumped somewhere by mistake. Let's double check here what happened. Okay, let's try to like reduce the complexity here. So let's go back to 2 CPUs. Run with GDB. And so here, what happens? He saw when he found CPU ID 0, then he tried on CPU ID 1, he tried to do some shit. And that's when everything goes to shit, presumably. Double checking. Yeah, so he gets to CPU ID 1, things go to shit. And if we backtrace here, we're in a copy from a vector from address 0x00000. So he's just like fucking confused. So let's start just like, let's try only setting the, oopsies. Let's try only initializing the CPU. Right? Let's see if that does anything. And we wait for wait for it to be delivered. Break it down till we see something that makes sense. That already is fucked. Okay. And our backtrace here. It is just stuck. Let's think about this. How can we debug what's happening? I guess we go into GDB and we just set a breakpoint at the start of this and start trying to work through it. I guess it would also help if we were not in release mode, except I think that release mode our debug mode was already busted from some incorrect shit we did the other day. So let's try this, I guess. Source run.gdb. So he never gets to that line? Interesting. Oh, wait, hold on. I'm using the wrong kernel here in my GDB script. Oops. So let's try this again. source, GDB, we launch. There we go. If I hit continue now and where are we we're getting stuck on wait it be delivered. Okay, this makes more sense. So what we had before was we were using the wrong binary to run GDB with, and we were just getting like garbage addresses. Here, getting stuck in wait it be delivered makes way more fucking sense. Okay. So there is a good chance that this shit just isn't. So here we saw them injecting some ASM pause memories in here. So let's just do the same here to see if that changes anything. Pause. And I have to flag that this affects memory. So is there like out in our Rust assembly thing? Is there a memory output? Inline assembly. Somewhere here, they must say memory. Laid out, in out. You can write register, or can you write like, can you just write memory in there? Mem, maybe? I'm sure I've seen it before. Out reg expression must be possible, blah, 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 underscore, maybe use instead of expression. Rust ASM memory output. I just want like somebody to just tell me the answer. ASM outreg, inreg outreg, late output, explicit register, clobbered registered, symbol operands, register template modifiers. Yeah, nothing in here. No mem means that the ASM goes. So I guess memory's on by default. Sure. So here I'll just write pause. And let's see if that changes the behavior at all. Cargo, run, release. And here I source run to reload my GDB setup. He is stuck, and if I backtrace, I am still on wait it be delivered. So where does this delivered come from? This comes from a volatile read of the low ICR low. So if I should be able to say ICR low read volatile, maybe I have print line delivered here every time, just to see. Or here we'll print the value. Oh, hold up. It gets deasserted if it's finished, right? Wait for delivery. Do this while... Oh, yeah, while it's set. Ah, fuck. Yeah. I'm just getting it backwards. I've got if delivered break. So if undelivered... Continue, else break. Oops. Oopsies. Okay, let's try that. Which means that we can uncomment a lot of this shit and see if we start getting something else. Cargo run. We source our little script again. Oops. He's already running, so we gotta reset him. Source this. Continue. Okay. So now Okay. Wait. That's really good. So here we now in GDB think that CPU 1 is running. That's really good. So I think that you can like break on address 0x8000. Yeah. Oh yeah. Okay. And now if I let's edit my GDB script, I guess, to put that in here. So we'll just say break at 0x8000. Run release, source my script. And I don't get a breakpoint there. Oh, because he thinks it's a function. Oops. What was it? Break star? Yeah, you have to put the star in there. Okay. So here, I put a star here. Rerun. Run GDB. Woo! Let's go! Okay. So this does hit me a breakpoint at 0x8000. Like I'm hitting... Oh, this is sig trap? Maybe that's not the breakpoint I wanted. If I delete that breakpoint and restart, do I get the same thing? Hold on, let's see. So let's run GDB. So here, if I set my breakpoint, I do get a trap there. But if I don't set the breakpoint, I think with a comment like this, do I not breakpoint? Yeah, okay. So that's a really good sign. Very good sign. So the fact that we're getting a breakpoint, the backtrace isn't right because I guess because which makes sense because our registers are not set to anything sane at that point, right? We're just gonna like launch the CPU. So it kind of makes sense that when you type like backtrace or like where the fuck am I, he doesn't know because his stack pointers and stuff, but his instruction pointers should be. Can I print the instruction pointer at that point? So let's cargo run release. And here, let's run our GDB script. And I think that there's like a way to like info regs. GDB print regis instruction pointer. Layout ASM. No source available. Great. Of course, that makes sense. Oh, here, display program counter. How do I get back? Ooh, fuck. One more time. So here I want to print program counter. I just want to like dump registers. GDB. I'm sure there's like a info registers. Yeah, info registers. Oh, oops! I typed regs last time maybe instead of registers. None of these are the instruction pointer though. GDB instruction pointer. I don't want the current assembly instruction. I want like just literally PC. It's possible that PC just isn't like it doesn't look right. Right? It says 0x0, but it's possible that like because our entry point here is just like fucked that it doesn't get set. Can I go like next instruction? It does seem like why does it think it's at 0x00000? Maybe because like whatever happens to be in the binary at where we're jumping to is just fucked. So, okay, so what's next? Can we like prove to ourselves that we're doing something interesting? I guess we can just copy paste the trampoline code without really thinking about it at all. just assume that this is doing something sane, which we've kind of like vetted to some extent. Stick this at the correct location and see if like it runs. That doesn't seem unreasonable. What else could we try to do? We could try to like in assembly just like exit the virtual machine and see if that is visible from yeah, I just want to like see like any visible effect. I guess we'll just start with the easy shit. We'll just start copy pasting this whole thing and see how we'll move on from there. So here we've definitely proven that some code is running, right? We've proven that the CPU is initialized, I guess we'll say. Prove CPU second CPU initialized with GDB, and we'll say that's at like an hour 22 into stream. And then we'll try to like prove assembled code running on second CPU. That's what we're working on next. Okay. So what do we want to do here? We want to ask our linker to put some code at that address. So we can look at our boot.s, our only assembly file in the whole project. And let's just like make a new section. And we'll call this like trampoline. And we'll just drop the shit in here, right? And here we're gonna have some like undefined symbols, so we'll deal with that in a sec. And here in our linker script, I think what we want to do is we want to say here is equal to 0x8000, right? So we're just gonna say like put us at this address, shove our shit in there, right? So that's gonna be a text section, maybe with like I don't give a fuck about like alignment. And here, well, we can write that in there. That's fine because we know that this is a 4K boundary. And what can we put in this? This is the trampoline section. So if I cargo build release now, there's some issues in here for sure. And does it not like these like comments? What the fuck? Yeah, it doesn't like these comments for some reason. Okay. That's fine. We'll just delete them. Okay, so we built. And maybe what we'll do is we'll open GDB with target release kernel, or target, I think it's target release kernel. And can I like, I think there's a way to like just print the disassemble. Disassemble at this address. Dump of assembler for the, okay, can I disassemble like at this address? This doesn't look right. Disassemble at specific address GDB. I'm sure there's a way to do this. X I at this address. And can I ask for like many instructions? Oh, disassemble start address end address. Okay, let's try that. Did I fuck this up? Disassemble start address end address. Oh, dis-ass. Maybe I spelled it wrong. Dis-ass, man. Expression error near this. What the fuck? Does he have an example? Yeah, so why? What does he think a syntax error is? GDB disassemble syntax error. Am I high? Like, what am I missing? This is what I just wrote. It does work in some circumstances. Can I maybe X multiple? Can I like XI 68000? First of all, is that even what I've written here in my boot script? No, the first thing that we should see is a clear instruction. Oh, fuck. But this is in 16-bit mode, so we actually can't tell. Can we look at maybe 8040? That also doesn't look right. So it's also interesting here that we're seeing like symbols that are theoretically, like supposedly part of something else. So it's possible that our linker script didn't do what we thought it would. Let's look at this again. Maybe we'll obj dump our kernel. And do we see anything in here that resembles? So here we see some early stuff. Why does it think that the text section is so early in the binary? I must have fucked up my linker script. So let's just maybe comment out this stuff. Or delete it and look at our obj dump again. Oh, interesting. So why does it think that there's stuff there at all? Oh, is it just not rebuilding? Fuck. There's a good chance it's just not rebuilding. Because it doesn't know that the linker script is like part of the build. So maybe what I do is I go into main and I just like edit a line so that it forces a recompile. Okay. So we are still seeing a bunch of stuff at 8,000, which is not what we want at all, right? So let's delete this, I guess, all of this stuff, and go back to how we were before. And build release. And obj dump again. Okay, so this is more reasonable, right? This is what we wanted to see before, is that we had kernel starting at like 1 meg, and we just wanted to add a little bit of extra stuff in our linker script before that. So I don't really understand why that's a problem. Maybe did I put the wrong thing here? Can I just say like trampoline takes in trampoline? Do I need to, and then put this at 0x8000? Maybe I also have to set like 1 megabyte within one of these blocks. I'm not really sure. Let's try this again. So obj dump. Oh, it doesn't rebuild, obviously. So whoa, we build release and obj dump. Build release. He actually rebuilds. We do an obj dump. Come on, baby. Oops. Ah, fuck. Obj dump. Okay. That's a good sign. Can I do obj dump shows, I think it's like S for everything with symbol trampoline on target release kernel. Not found in any input file. Okay. What if I like flag this as text and say this takes in the things that we said was trampoline before? Oh, I have to go back in main and edit this again. Cargo build release. And obj dump. Okay. So we have a bunch of stuff at 8,000. Oi, 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 oi. Maybe I need to do some Googling here. So how do I like look at my linker script docs? Linker script add segment. Linker scripts. It's been a while. This is, oh god, linker script docs. I don't know. Someone's got to tell me. Linker scripts using LD scripts. This looks promising. Basic linker scripts concepts, linker script format. Oops, sorry. Punch the mic. Here we go. Example. So here they do let us set multiple sections. Second defines the output section text. Colon is required syntax. Within the curly braces is the names of the input sections should be placed into this output section. Can I have like multiple text sections? Linker script multiple text sections. I guess, okay, let's go back to the linker script defining this as trampoline. Because that seemed like it was like the closest to working so far. So we build, we obj dump, and we put this bunch into less. So the weird thing is that it seems to like be deleting stuff. Obj dump help. I don't know why my man page isn't working, so we'll man obj dump on the internet. And what I'm looking for is like, how do I just like print everything? S, lowercase s. I was using uppercase s. Oops. Which I actually don't know what that does. Source. Ah, fuck. Okay. What I've been trying to type this whole time is obj dump -s. And here we're showing the text section. This is, can I look for like 8,000? Or can I look for like trampoline? Is there like a section trampoline here? Linker script deleting section. Oh, I think I've seen somewhere a like flag for stripping arguments. So let's just double check which flags I'm sending to my linker here. I think it's under cargo. Here we have target JSON. Here we set some linker options, and we're not really setting anything significant. Linker strip sections arg. Strip unused segments, maybe. GC sections. This is what I want. This is what I was thinking. So how do we like remove? Let's just double check if that's on. So if I cargo build release and I'm with verbose mode, can I like cargo print linker command? There's got to be a way. Yeah. This looks maybe like it. So what is he saying? How do you get the LD linker to be verbose when you use cargo? I guess this isn't what I want. Maybe it is. It doesn't show linker invocations or anything else. Oh, I see. Print link args. Yeah. This is what I want. This is what I want. So here we'll cargo build release. And here we'll edit main again so that it recompiles. Ah, yeah. So now we should be able to see if we're passing in like a garbage collect. Yeah, motherfucker. He's GC section thing. Which is probably deleting my trampoline section. Garblic. So how do I remove? Can I like delete? Can I like specify sections that I don't want deleted with GC sections? GC sections keep section. What a. Ooh, okay. Okay. So maybe they're saying that here I just write keep in my linker script. Right, they're writing keep somewhere. So can I just write like keep like this? We edit main again. Cargo build. He finished. And can I print this now? Okay, let's scroll through this now. Do I see like an 8,000 anywhere? Womp, 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 womp. Oh, okay. So here at 8000, that's not very useful. What am I even looking at here? Contents of section debug look. Ugh. Maybe I put this. Maybe I do something like this. I have my text section. I put the pointer to 8,000. I throw this shit in here. Then I put us at 1 meg again. Maybe? That doesn't seem crazy. And then maybe my trampoline code will be in the right spot. So let's go back to main, modify the scans that when I build it, I actually see something. Oh, I guess I don't want this linker line in there anymore. And objdump -x for, no, objdump -d. And then less. Yeah, this is getting fucked up. Oi. Yeah, that's clearly wrong. Clearly wrong. All right. All right. This is annoying. I really thought this would work. I really did. So if I like build this at all, oopsies. Oh, damn. I was really hoping that I would just be able to get the linker script to punch it in there for me. Really was hoping. Yeah. So am I even seeing my like AP trampoline stuff? Maybe I need to set this as global. Right? Maybe like the fact that it thinks that this isn't referenced anywhere is causing an issue. Yeah, I don't have a good answer. I don't have a good answer. Okay. I need to do some like reading about linker scripts. I'm kind of annoyed that this isn't working, and I don't really want to do this bullshit that they did in their version where I really don't like this mem copy. It seems like I should be able to get my linker to put the code I want in the spot I want in a way that I can run it. But I just don't know it well enough right now, and I'm probably gonna have to do a lot of reading before I get that answer. So I am pretty pleased though with the fact that we do have like some form of indication that we've booted the second CPU, even if it's just executing garbage code and breaking. I'm pretty happy with that. I think, yeah, I'm gonna do some offline reading to try to figure out this like linker script stuff, and we'll come back tomorrow and just hope that we can get the linker to put the code where I want it, and then actually get some code running on the second CPU. Otherwise, yeah, pretty happy with what we accomplished today. Wish we could have got more, but that's okay. It's part of the process. So if you liked what you saw, feel free to tune back in tomorrow. We're going to keep going. So I stream most days between like 1 o'clock or 2 o'clock p.m. Pacific time for like 1 or 2 hours. If you miss, you can always catch up on YouTube. So the YouTube is linked in the Twitch description. And if you're watching on YouTube and you want to pop by, say hi, ask questions, whatever, Twitch channel is linked in the YouTube description, and I just said the times that we stream at. So thanks for watching. Catch you in the next one. Bye.